All right, everyone, let's get started. Today, we're tackling a super important topic from Unit 2. That's electrostatic potential and capacitance. And the topic is the parallel plate capacitor. Now don't worry, I promise we're going to make this so simple you'll remember it forever. And, most importantly, it's going to be perfectly exam safe.
So let's jump right in, but before we get into the formulas and definitions, I want to start with a question to get you thinking. Why is this topic even important? Let's look at something you probably use every single day.
Have you ever wondered how a simple condenser mic, like the one I'm probably using right now, can hear your voice? Well, the secret, it's all physics. You see, inside many of these microphones, there's a tiny parallel plate capacitor. One of its plates is this super flexible thing called a diaphragm. And when you speak, the sound waves from your voice literally make this plate vibrate back and forth. This changes the distance between the two plates, and this constant change creates a changing electrical signal, a signal that's a perfect copy of your voice. How cool is that?
So to really get how this works, I want you to forget all the complex physics, just for a minute. Let's use a really simple analogy, and I promise you, once you hear this, you will never forget what a capacitor is.
Seriously, at its heart, a capacitor is basically just a simple sandwich. I'm not kidding. If you can picture a sandwich, you've already understood the basic structure of a parallel plate capacitor. See, it really is that easy.
Okay, so look at this. What's so cool is how perfectly this analogy works. The two slices of bread, those are your two parallel metal plates. One plate has a positive charge, we'll call it plus Q, and the other has an equal negative charge, minus Q. And the filling, the cheese or the veggies in between, well, that's just the empty space, or the gap between the plates, which we call D for distance.
All right, the sandwich analogy is great. It's perfect for understanding the concept. But you can't write about sandwiches in your board exams, right? For getting full marks, we need the official stuff. So let's look at the proper NCERT definition and see how it builds on our simple idea.
Okay, here it is. This is the exact definition from your textbook. A parallel plate capacitor is a system of two large, plain, parallel conducting plates, separated by a small distance. The key words you have to remember for your exam are two large, plain, parallel conducting plates. And the distance between them, it has to be small. That's it. That's the definition.
And here's the formula you absolutely need to know. This is the exam-safe formula, C equals epsilon naught A over D. Now, this formula, it just perfectly captures the whole idea. The capacitance, that's C, it really just depends on two main things. A, which is the area of the plates, and D, the distance between them. That funny-looking symbol, epsilon naught, it's just a constant, a fixed number. It's called the permittivity of free space. Don't worry too much about it for now, just know it's a constant.
Now, look, this formula isn't magic, okay? It didn't just fall out of the sky. It actually comes from some very simple logic. Stuff you've already learned in Unit 1. So let's build it together step by step. There are just 4 easy steps, and if you follow along, you'll never have to just blindly memorize it ever again.
See how it all fits together? It's so logical. Let's go through it. Step 1. We start with the electric field E between the plates. You remember this from Unit 1, right? It's just Q divided by A times epsilon naught. Simple. Step 2. The potential difference, or voltage, V, is just that electric field E multiplied by the distance D. So V equals E times D. Step 3. Now we just plug the first equation into the second one. That gives us V equals Q times D all divided by A epsilon naught. And finally, step 4. We know the basic definition of capacitance is C equals Q over V. So we just rearrange that equation from step 3 and boom, we get our final result. C equals epsilon naught A over D. See? It's all connected. No magic, just physics.
Okay, quick thought experiment for you. This is a very common type of question you'll see in your exams, so listen carefully. What happens to the capacitance if we double the area A of the plates and we cut the distance D in half? Think about the formula. What happens? Did you get it? The capacitance becomes 4 times larger. 4 times! So why? Well, think about it. C is directly proportional to area. So if you double A, you double C. Simple. And C is inversely proportional to distance. So if you have the distance, you actually double the capacitance again. So you get a times 2 from the area and another times 2 from the distance. 2 times 2 is 4. Easy marks.
Okay, now for a really important part. Let's talk about the common traps, the silent killers, that cost students marks in the exam. These are the small mistakes that can really hurt your score, so I want you to pay very close attention here.
Here's a big one. A really common mistake is thinking that the electric field outside the parallel plates is also strong. You know, students think, well, there's a strong field inside, so there must be a field outside too. Let me tell you, that is a very common and a very wrong assumption.
So what's the correct physics? It's actually really beautiful and simple. Outside the plates, the field from the positive plate and the field from the negative plate point in opposite directions. So what happens? They almost completely cancel each other out. The net result is that the field outside is approximately zero. They just cancel.
Here's a little memory hook so you never get this wrong in an exam. Just remember this simple phrase. All the action is between the sheets. The important electric field, the one that matters, is only between the two plates. Got it?
Fantastic. Okay, let's wrap this up. We'll do a quick summary of what we've learned. And just as important, we'll see how this topic connects to everything else you're studying, to get the full picture.
So you see, this topic builds directly on what you learned in Unit 1, specifically the concept of the electric field from an infinite plane sheet. That was the foundation for today. And what we've learned today, well, this unlocks the next big topic, which is the effect of dielectrics on capacitance. That's when we ask what happens when we put stuff inside the capacitor.
So for your exam revision, here are the key takeaways. First, the key formula. C equals epsilon naught A over D. Second, the proportionality. Capacitance is directly proportional to area. Third, the inverse proportionality. Capacitance is inversely proportional to distance. And finally, the field. The electric field inside is uniform and strong, but it's basically zero outside. That's your checklist.
So we've totally mastered the capacitor with just air or vacuum in the gap. But that brings up a really interesting question. What happens if we fill that gap with something else, like, say, a sheet of plastic? How does that change its power to store charge? Well, we're going to explore that fascinating question in our next explainer when we dive into the world of dielectrics. All right then, I'll see you in the next class.